Newton's third law is usually the most well-known in our everyday lives, but it's also the one that's the most misunderstood. Because you've probably heard someone say before that for every action, there's an equal and opposite reaction. And that technically, in a sense, kind of gets at what Newton's third law is, but it's really not descriptive enough to get the details of it. So Newton's third law in its complete form says that object A, if it applies a force onto object B, then that object B, that second object, will apply an equally sized force, but in the opposite direction, back on object A. So if you're following that definition, you might think it sounds very similar to the idea that for every action there's an equal and opposite reaction. But the reason why we use the complex definition is because we need to take into account that there are two separate objects. And these equal and opposite forces are not acting on the same object, but they are each acting on a different object. From there, though, we can actually use this law to explain lots of everyday situations, and even some situations that maybe aren't so common to our regular experience, but can give us some understanding into the law in more detail. So for example, if we look at an astronaut out in outer space, so if that astronaut's holding a wrench and floating in space without a jetpack, what could the astronaut do if they wanted to move towards the left? Well, you probably have some idea that the wrench is going to play a key role in this. So let's think about the forces involved. If the person wants to move to the left, let's imagine that this astronaut throws or even just pushes. So if we throw or push the wrench to the right, well, let's think about what would happen there. Why am I mentioning throwing the wrench to the right? Well, remember, throwing or pushing the wrench is the one object, the astronaut, applying a force towards the right on that wrench. Well, what does Newton's third law tell us? It says that if that happens, then the wrench will push back, or push the astronaut back towards the left. So that's the idea and how Newton's third law can help us to explain this. So if we throw or even just push that wrench towards the right, that wrench must then apply an equally sized amount of force back onto the astronaut, which would push them back towards the left. And again, remember, it's two separate objects. The wrench experiences the force to the right, while the astronaut experiences the force to the left. So if we stay on the outer space theme, we can also think about what a rocket does when it blasts off. Now, we know that it's applying some force backwards. It's shooting some jet fuel out the back. And then there must be some force pushing it forwards. And you may think that this force comes from the ground. Maybe the ground pushes back up, kind of like normal force, because we would picture this thing blasting off from the ground. But rocket boosters actually would still work and can propel a spaceship even when it's off the ground, even when it's already out in space. So how is it that those rocket boosters could actually do that? How do they propel something forwards? Or in this case, we'll say, how does it propel the rocket upwards? And so we can actually do this even without talking about the ground whatsoever. Because remember, there are actual particles of fuel being expelled out the back of these rocket boosters. So let's mention that. The particles in the jet fuel are shot downwards in this case. So that's the one object, the rocket, applying a force to the jet fuel to push it downwards. And the jet fuel, it's a whole bunch of small particles, but you can imagine it to be sort of one common object, a collection of particles combining together. If they're shot downwards, we know they need to apply a force back onto the spaceship itself, onto the rocket, in the opposite direction. So the particles push the rocket upwards. They apply an equally sized amount of force in the opposite direction to what they are being pushed. So again, the two separate objects, if we want to think of it that way, one is the rocket itself, the other is the jet fuel combining together into what we could think of as one large object, really a collection of particles. So the rocket ship pushes down, and the jet fuel pushes back up, and that allows the rocket to actually move upwards. But I did promise that this law can help us to understand some things in our everyday lives as well, and you're probably not as familiar with blasting off in a rocket or being out in outer space without a jetpack, but you've probably walked before, and you probably didn't realize that the only reason why you are able to walk forwards is because of Newton's third law. So when we think about what happens when we walk, you're applying a force to the ground. So the ground is below you, and we think of ourselves as pushing down on the ground. But how does that allow us to move forwards? Well, as it turns out, and you can analyze this yourself if you look at yourself the next time that you walk forwards, really focus on what your feet are doing. And I challenge you to try and walk forwards without any of your foot pushing backwards at all. We always do it without realizing, but as we walk forwards, our toes actually push backwards on the floor a little bit. Even though we're also, of course, pushing downwards, the main thing that's helping us to move forwards is the fact that our toe, or at least part of our foot, pushes backwards on the floor. So we push backwards on the floor. With your feet, or at least one foot at a time. So the floor pushes your feet forwards. And again, each foot and the ground are representing the two separate objects. So you have one foot that's pushing backwards. That's your foot applying a force in one direction backwards onto the floor. And so the floor, being the other object, applies a force to push that foot forwards. And both of your feet end up doing this in an alternating fashion. And again, you may not believe me that your feet are always pushing backwards, but that is the challenge that I put to you. Try to actually walk forwards without any part of your foot in any way pushing in a backwards direction. It's actually impossible to do, and you may not have ever realized that. Now, the very last example, this thing about the cart and the horse that you see listed, I'm going to go through in class. You can try and read through the description if you want and make some sense of it, but don't worry about it just yet because we are going to go through it in more detail in class. But it's a really important example to get at this very important distinction that I keep harping on, which is that this law is only true when we're talking about two separate objects interacting with one another. And we'll get into that more with the cart and the horse example, as I said, in class.